So, yes, my pleasure to introduce Shorouq Zahra, RISE, a research engineering and development at RISE Research Institute of Sweden with a focus on NLP, conversational AI. And she has been engaged in the work using LLMs to build a database of climate extreme impacts that was presented at the Climate NLP 2024, proposing a method for building large-scale databases of climate extreme impacts from online textual sources, using LLMs for information extraction in combination with more traditional NLP techniques to improve accuracy and consistency. Her talk today is titled "The Challenges of Using LLMs to Extract Data on Extreme Climate Events." Thank you.
Thanks for the introduction. So welcome everyone. I'm going to tell you about the challenges of using LLMs to extract data, and specifically when it comes to the impact data of extreme climate events. And most of this presentation is going to basically walk you through the different challenges in the process of creating Wikimpacts. And Wikimpacts is a database of extreme climate event impacts that was sourced from Wikipedia, hence the name. And we have to legally say that we're not associated with Wikimedia. And it contains information on about 3,000 different climate events and their impacts on human society. And it uses an LLM at its core. Hence this presentation. Right. So one question I like to ask myself is, do we even need AI at all to solve a specific problem? So, and this could be a question that continues with me as well, but right now, there are some databases made by humans, obviously, but when we look at them, we realize that we do need better ones. So the current databases tend to be incomplete, and they tend to have a lot of gaps. Here's one example from EMDAT, the emergency events dataset, a quite popular dataset if you're trying to model climate impacts. And it's a map of heat waves between 1953 and 2012. And you notice straight away that something is missing, which is the heat wave data for most of the, maybe all of the African continent, right? So even though we know that Africa is generally prone to heat waves, we also know from research that in the past 2 decades, the heat waves have actually worsened there. This is not captured in the statistics up to 2012. And don't be too harsh on the EMDAT people, it's really not their fault. It's just what happens when you get data from some sources, right? So I'm sure at this point you're like, but there's probably other data sets that you could use. And when you actually look at some of the impact data from different data sets, we find that it can be quite inconsistent. So for example, here is data about windstorms taken from 4 different data sets or developed by 4 different institutions or groups of researchers. And this is the insurance loss from these windstorms in Europe, or I think most of them, right? And it's normalized between 0 and 1, so we're able to compare. And we can see straight away that for some of these windstorms, the amount of insurance loss that they considered, depending on their sources and so on, was close. But for some of them, there are really major discrepancies, even though they're all looking at the same storm. So the same occurs for all sorts of other kinds of data that we need, especially data related to the hazards of impacts. I will get to that at some point later on this presentation. The third biggest motivation as to why to use an LLM to do this is that it actually takes a lot of work to create a data set. So oftentimes with these data sets, someone is employed to read all of these climate reports and try to extract this data from them and put them together in a database, maybe do some quality check. So if a human was going to just read a big block of text and extract information from it, why couldn't we get an LLM to do it? And maybe even as reliably as a human can, right? So I'm going to take you through 4 main challenges of how we made the database, and this was the first one that we faced, which is that the data was actually quite tricky to represent. So here is Wikimpacts in a simplified format. We take some kind of climate event, let's say a tornado or a wildfire, and we make the LLM extract stuff like, where did it happen? When did it happen? What kind of hazards were associated with it? And then we also wanted to get us some information about the hazards, the fatalities, the injuries, how many people were made homeless, how many people were displaced, how many buildings were damaged or destroyed. And we also look at the economic damage, so how much did they have to pay in damages and in insurance. And we actually represent these numerical pieces of data as a range between a min and a max. Right? And also for the economic ones, we have to get stuff like currency, when was the inflation adjusted, and so on. And this is only the simplified view, so it gets more complicated. It was not enough to have this data just on this event level, but instead we had to also go down a few location depths, if you like. So for this L1 or level 1, we basically say, okay, some kind of flood happened in Europe. It maybe killed, let's say, 30 people in Germany, France, and Belgium, right? But you might be a climate scientist that cannot just work with this overall data, but you want the specific numbers for Germany, the specific numbers for France, and so on. So then we had level 2, so we also extract information based on that. And then we go down one level even deeper, and we try to get information about different towns and cities and how many people were affected there. And then we actually hope that the LLM has actually extracted numbers that make sense. So if you sum numbers up from different countries, we want this L1 to be consistent, which made everything a lot trickier than we thought. The other problem, or the next problem that we faced, is that we started experimenting with LLMs, and we noticed that they don't always give you consistent output. So this is a simplified version of our data, of our pipeline for Wikimpacts. We start simple. We get some documents that we want to feed to the LLM, and these are documents that have to be about climate events, right? So we first used keyword filtering, and the problem was that we would find a lot of things that were not really hurricanes or not really tornadoes, such as the Miami Hurricanes football Wikipedia page. So then we also had to get a fine-tuned BERT classifier to take some of this rubbish out and just give us very relevant documents, right? And then came the fun part. So now we thought, okay, we give this text to the LLM, we give it a really nice, long, detailed prompt, and hopefully it will give us all of the information that we want in very nice, consistent JSON. So we would ask the model to be as specific as possible. So if the article claims that there were no injuries, then it has to be able to translate this idea into 0. So it would return a JSON object saying injuries 0. But if the article mentioned no injuries at all, then we also want to know that the information is absent. So the model has to return null, meaning there's nothing there. And the model had to do this for all of our 3 complicated levels. Here is a bit of a, it's an image kind of showing this for the European floods of 2021. And at this point, we were hoping that the JSON was actually good, the information made sense, and the model extracted everything perfectly, and all the numbers were floats and integers, but this is not what happened. Instead, we had to actually add a last layer to our pipeline, where we post-process or clean up everything that the model messed up. And finally, we output it into an SQL database. So in this post-processing step, we actually had very rule-based approaches. We used more traditional models. We used part-of-speech tagging and so on to try to take the stuff that the model kind of extracted in an okay fashion and make it better, make it standardized. So first, there were lots of broken JSON that we had to fix or drop. And yeah, you know, ChatGPT is good when you just want help with an email, right? It can say please and thank you and give you the answer. But when you actually wanted to extract everything in a specific way, it gets quite tricky. Then we had the problem with dates appearing in a million different formats. Thank you, the Americans, for this. So we had to, but of course there were articles, you know, from different places, so people had dates in different ways. And then we had stuff like the model would return things like over 47,000 buildings were damaged. And this is a problem because it's an interval. So where do we start and where do we end? So we had to kind of translate this into some kind of range of numbers. So we translate this into an estimate. And finally, we got the locations from the model as strings, and we had to actually turn them into borders on a map so that people could use them for modeling. So here's a very quick example of a post-processing. On the left, you can see what the LLM gave us. So you can see that it says stuff like between 20 and 25 people were killed. I think most of this example is pretty much verbatim or real. And then it says something like, this happened in the UK. Well, that's not good enough. We have to actually change it into Great Britain and so on. And all of the locations we also had to turn into a GeoJSON, which is a really nice format. It's a JSON file that encodes the coordinates of a place, whether it's a point or a polygon or something like that, on a map in a nice and cheap way. And this would not have been possible without OpenStreetMap and a bunch of other databases. And I think someone here was from OpenStreetMap or contributed, so thank you. Yes, thank you very much for that. And here I'm just going to take a moment to thank all of the non-LLM tools that helped make this post-processing happen, especially Regex. Regex, I love you. It would not have been possible without you. Thank you. So yes, so there you have it. This is what we kind of have to, this is what we had to do. So it really shows you that it takes a village to make an LLM behave properly to get the output that we want. So the next problem was, how do we evaluate the system, right? So our first step was to get a bunch of people in this field, and they annotated a bunch of events from Wikipedia and some other sources, but in this first release we focused on Wikipedia. We made them double annotate some of these to see how much they agree. And if you remember the levels of depth that I told you about, for the top level, everything was fine. Then when you start going down in the levels, the agreement got worse between these annotators. And they complained a lot, because back to the first point, it's actually quite difficult to make these databases, right? The annotations were tricky, the articles were unclear, there was lots of disputes about what should be where. And we ended up with 70 articles to develop our prompts and post-processing, and we also had 156 to test on. And we had to decide on some kind of metric to use to tell whether the information that the LLM extracted makes sense or not. So we thought, okay, if 10 people had died, and the LLM said 11 died, well, that's not a big difference. It's not going to make a big it's not going to cause a big problem in the big scheme of things. But if the model accidentally adds a 0 and says hallucinates that 100 died, then it becomes problematic, right? So we have this distance measure between the annotated and the retrieved, and it's quite simple. So if we're asking the model to return a list of location names or something, we use Jacquard distance. And sometimes it's just exact matching. So we just want to know how far off we are from the truth. And so the first model that we started with was GPT-4o, because it was available and easy to use. And our main researcher who was working on it really liked using it. It helped her get started very quickly. So it was doing a fairly good job, as you can see. So one thing I want to mention, that 0 is actually good. So the closer the numbers to 0, the lower the error rate. And vice versa. So we can see that for most of these categories, GPT-4o is doing great, except for locations, which is called administrative areas norm or normalized. But the problem is, do we really need commercial models for this? Because we created a pipeline that we essentially want to be reproducible and that people can do, hopefully, on their local machines, so they wouldn't need to rely on us, right? And one of our researchers that we worked with, that mainly worked with GPT-4o, she actually had to get a grant for thousands of dollars from OpenAI themselves to be able to use their models. So it's quite costly to do this. And then comes the baggage of OpenAI and the problems that they are causing the research world, because we actually realized that we cannot trust them. Originally, we started even with GPT-4, and then our researcher moved to GPT-4o. But if we had continued in the track of GPT-4, our pipeline would not have worked now, because Sam Altman decided to send it out to retirement. So GPT-4 is gone, right? So we thought to ourselves, well, you know, we have all these awesome other models that we could use out of the box. And this does not look good. So most of this table is red. So the darker the red, the higher the error rate. These 1, 2, 3, 4, 5 open source models got when compared to GPT-4o out of the box. But we thought to ourselves, well, you know, we have them locally, we have the weights. We can train them in different ways. We have Hugging Face transformers, you know. So we decided to fine-tune them. And straight away, as we fine-tuned Quen and Mistral here, we noticed that they already improve on their own score. So they were already doing such a good job. Just out of the box, just fine-tuned compared to the out-of-the-box model. But you might want to say, okay, well, how does that look like compared to GPT-4o. Here's the table for you. So actually you can see that Mistral, which has 24 billion parameters, this is called Mistral small for some reason. Don't ask me why. Which is much smaller than GPT-4o, or we don't know, it's a mystery, right? Is already performing in a quite competitive fashion. Yes, it does have these problems right here with some specific categories like insurance damage and so on. But you know, overall it's doing good. Quen is not doing so great, but it also did not diverge from the GPT-4o score so much. This brings me to the final challenge, is that when we were done creating this database, we looked at some maps that we had from it, and we noticed some of the same old gaps and maybe some new gaps. So we still have a problem with the African continent. We still don't have data there, for example. Our biggest idea now is that this is probably related to Wikipedia bias. So this is related to the sources that we decided to get this data from. So thank you for listening. If you want to come in contact with us, so Ni is the main PhD researcher working on this at VUB. Feel free to write her. And here's my email as well, and Muratan Kurfali is sitting somewhere in the back. So if you have any questions or comments, please let us know.
Thank you. I'm going to take advantage of my role to ask a question before asking you guys.
Sure.
When you plot the maps at city level, region level, and so on, I noticed that you do have, it seems, a lack of coverage of cities in South America.
Yeah.
Do you think it may be because of the language difference, that you're somehow capturing a Spanish-English issue in Wikipedia, maybe?
Absolutely, and that is why in the second version, one of the plans is actually to expand it to Spanish, Chinese, and French. But still, there are some places in the world that do not really use Wikipedia in the way that the Western world does. One example is that there was a terrible flash flood in Jordan, where I'm from. And it was one of the worst flash floods in the history of the country. A whole bus of school kids just got taken away with the tide. And that is not on Wikipedia. So one of the worst flash floods in the history of my country were not found in Wikipedia. So where is it? So the idea is we need to expand this to models that can handle multiple languages and that are able to get this information from all sorts of sources. Wikipedia is easy because it's structured nicely, and the volunteers, they have standards for what they write and so on. But for other news sources, it could be, like for news, it's a bit more difficult to do that.
Yes. I'm going to go there. I'm very slow, but I'm coming.
Hi, thanks for a nice presentation. So on the comment of Wikipedia being structured, wouldn't you be able to do this with Sparkle queries on Wikidata?
To be able to extract the articles that are relevant, or I think so. At that stage, I had not still joined. My colleagues were trying that. For some reason, it did not work for them. But that was my initial idea as well, because they actually categorized their articles in some way. But unfortunately, it did not work out for them, which is why they went for the keyword filtering and the BERT. I don't know why either. So it must have been some kind of,
Just a quick comment. I think one problem is that Wikidata has much lower coverage than Wikipedia itself.
Yeah. That's true. Right.
Anyone else? Yes. Oh, sorry.
Quick question. I noticed in your list of event types that some of them are going to go together, so to say, like you had floods and hurricanes, for example, as potential events. So how does your system deal with that? Like, do you have basically two different entries then for the same event, or do you also have this compound event as a subcategory? Or
What was the first part of the questions you
my
said?
point is, like what you were showing at the very beginning, what type
Yeah.
of event you have.
Yeah.
You had, for example, hurricane and flood
Yes.
as two different options,
Yes.
but usually a flood will follow a hurricane.
Oh.
So how is your event classified in that case?
So first of all, the event classification is just based on the LLM, so it is just generating this text based on the article. About compound events, we have not gotten to that stage yet, but it is something we think about because we just thought, okay, at this point it's important to get a database with impacts, and then at a later stage we can look at the more complicated relationships between these events and their impacts. So nothing, sorry.
So I will move to the first speaker. Thank you to our second speaker.